Hello, this is the next video in a playlist that I'm calling Hypothesis Testing. In this video, we're going to look at two examples. Simple versus simple hypotheses. When our data follows a gamma distribution, that's the first example, and then our data follows the Poisson distribution, that's the second example. So the first example, our data follows a gamma distribution with parameters alpha and beta. We're going to assume that alpha is known. We have a sample size n, and the beta parameter lives in the parameter space omega that has 2 points, beta 0 and beta 1. This would be our joint density, which is the product of the individual densities. And we want to create an alpha level test that maximizes power. Well, according to the Neyman Pearson Lemma, we want to set it up like this. So the null hypothesis is that beta is beta 0, versus the alternative hypothesis that beta is equal to beta 1. Now later in this, we're going to assume that beta 1 is greater than 0. But we don't need it for this. This test function always works. But when we take this test function and make it a little more simple or understandable, might be a better word, then we need to know which one is bigger than the other. And I'll point it out when I get to it. So first, let's divide both sides of this by f0. And then the likelihood ratio greater than some constant c, then it makes phi equal 1, which says we reject the null. And then if the likelihood ratio is less than that constant, right, because we've divided that over, if it's 0, then we don't reject. Let's look at that likelihood ratio. So the f1 of our data and f0 of our data, so that means we plug in beta 1 for beta in here. Now alpha is assumed to be known, and here f0 we plug in beta 0 for the beta parameter. Now this cancels, the gamma of alpha cancels. This I take the reciprocal to make it a positive exponent. This e function can be brought up front. We factor out of the sum of the x's and we're left with this. Now let's look at the type 1 error. So let's take the expected value of our test function, assuming the null hypothesis is true, so that's beta equals 0. So it's this probability. Now it's the likelihood ratio greater than c, right? So the expected value of this is 1 times the probability of it happening, 0 plus 0 times probability of happening, but the 0 makes it drop out. So we're just looking at this probability, which the likelihood greater than some c. Well, the only thing random over here are the x's. So if it's a constant, let's take it to this side. So we divide by this, take the natural log, then divide by this, and we're left with this here, that the sum of the x's, xi's, are greater than this constant. Now this is where we need this knowledge, right? Beta 1 is greater than 0, which says that this is positive. So when we divide that over, it doesn't change the sign. Now if it were the other way, so beta 1 was greater than beta 0, and we make this division, then the sign would change, which is okay. You just have to know that when you're solving for this. So we're going to call this constant, we're going to rename it C prime. You know, not the original C, but some other constant not equal to that one. So the probability that the sum of the xi's are greater than C prime, we want it to equal alpha. So note that the sum of the x's is also a gamma distributed as a gamma distribution with parameters in alpha and beta 0. Beta 0 because we're assuming the null hypothesis is true. So now we want to find this constant C prime that makes this alpha. Well, this is how you do it. So you integrate the gamma distribution with parameters in alpha and beta 0 from 0 to some number, and I'm going to call it g of 1 minus alpha because we want this whole area to be 1 minus alpha. Now why is that? That's because the area in the tail would be alpha. And so we set C prime to, actually it shouldn't be equal because it's not equal. but we're finding, so this isn't equal. So we're finding this relationship, and we want this number here, because it's that number in the distribution that makes the area in the tail alpha. And that's what we set C prime to be, right? Because then this probability, it being greater than that, is alpha. Now, the power of this test is the probability that well, so now the new test function can be written like this. Let me say that. So if the sum of the xi's of our data is greater than this, this critical value, that determined such that it makes the area in the tail, alpha, when the null hypothesis is true. This is it. This is the new test function. Now, the power it's the expected value of our test function under the alternative. So beta 1 is true. So we want the probability that y is greater than this critical value. It means we're rejecting the null hypothesis, of course, when we should. That's what power is. So it's the integral from this critical value to infinity of this gamma distribution with parameters in alpha and beta 1, right? We're assuming the alternative is true. And that's power. Now, I didn't have specific numbers, but the next video, we're going to do an R video simulating the size and the power for this test. Second example, we're going to assume our data follows a Poisson distribution, sample size n. Here's the probably mass function for xi. We're going to assume that the parameter lambda lives in a parameter space omega with 2 points, lambda 0 and lambda 1. The joint probability mass function would be the product of these, which is this function here, lambda, sum of the xi, exponential minus n lambda, divided by the product of these factorials. Now we want to create a test function with level at most alpha and have maximum power. And that's this. Neyman Pearson says set, simple versus simple hypothesis. The null is that lambda is lambda 0 versus the alternative is lambda 1. We're going to assume that lambda 1 is greater than lambda 0. And that's we only need that for down here when we're solving an equation. So the test function is this, 1 or 0 if this is the case. That's the Neyman Pearson limit. Of course, I like to divide both sides by f0, so we have the likelihood ratio greater than some constant c, or the likelihood ratio less than some value c. Now note that we're going to create a non-random test here, and that's probably what I'll do for most of the videos here out. Occasionally I'll put the gamma in there, which if they're equal here, the likelihood ratio is equal to C, and we reject with probability gamma, and watch some earlier videos in this playlist for more detail. But because it's a non-random test and our data is discrete, we'll only probably get close to the desired alpha level. We won't go over it, but we can only get close. We can't make it exact because it's discrete in this case. So let's look at the likelihood ratio. So we plug in lambda 1 in the numerator and lambda 0 in the denominator. Now things cancel. And so we get this ratio, and then E, we can bring it up and we get this. Now, let's look at the expected value of our test function under the null hypothesis, which is this probability. It's the likelihood ratio, which we said was this. So we're going to put this in here, greater than C. And then we solve for the random piece, which is this sum. So we divide, divide this over, take the natural log of both sides, and we get this. So the sum of the xi's are greater than this constant here. So now, because we know this, then the inequality stays the same, right? This is positive. It doesn't make it a negative when we divide it over. So we just call this some constant C prime. And so this is the probability that we need to find. But note that the sum of the xi's is again Poisson with n times lambda 0. It's lambda 0 because we're assuming the null hypothesis is true. So we need to choose C prime such that this probability is as close as possible to alpha, but not more. We don't want to go over that. And that's it. So that's how we pick C prime. Then, we can use a table in the back of a book or use the R software to find that value that makes this as close as possible to alpha, but not going over. Now, the power is the expected value of the test function, assuming the alternative is true, which then becomes this probability, the probability that we're greater than that constant C prime when the alternative is true. Now, note that if the alternative is true, this sum becomes a Poisson distribution, distributed with a Poisson with parameter n times lambda 1, because we're assuming the alternative is true. And then that's how you would find power. Just plug it into the R software. Now again, we're going to illustrate this example with the R software, and that's going to be the next program or the next video that I put out. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.